Okay, so here we have another Morin problem. I really like his classical physics textbook. This is number 3.43. And I am paring down the question quite a bit. I'm going to say it more than write it down. Morin says, imagine you're on this planet called Gravitus Increasicus. I don't know. Anyway, the idea here is gravity on this planet is strange. The moment you launch your projectile, gravity turns on and it grows stronger with time. So imagine that the gravitational field strength is a function of time, and in fact is a linear function. It's some constant we'll call beta times t, where t equals 0 is the time you launch the projectile. I have no idea how this particular planetary behavior would come about. Maybe this is an artificial planet. Regardless, the question is, okay, what is the range of a projectile on such a strange planet where gravity gets stronger and stronger with time? What angle theta, launch angle, maximizes that range? And maybe what is that maximal range? We might answer a couple other questions like, what is the maximum height that it obtains? What's the trajectory? We'll look at all of that. Okay, so as usual, we want to start by looking at kinematics. Even though the acceleration is not a constant anymore, it's a simple enough function that we should still be able to integrate and get our equations of motion, our kinematics equations. So in our particular case, we do want to say that x double dot is 0. We are not accelerating horizontally, so that means that we can use our usual constant, and in fact 0, acceleration kinematics equation for x. And like I said, this term is 0. The interesting one is the y direction. So notice that the y acceleration is negative. Gravity is still going to point down. But now the gravity changes with time. The acceleration is not a constant anymore. So we're going to have to integrate this a couple times to get our y of t. Let's do that in 2 steps. First off, the first derivative, which we could also call vy if you want, is just going to be a single integral of this. Now don't forget that when you do these integrals, we do have a plus c. In other words, we have a constant of integration. But that constant is just going to be the initial y velocity. So I'll go ahead and write that as vy naught. Maybe v naught y, just to match what I have up there. And then the antiderivative of this linear term will be minus a half beta t squared. Okay, so that is my velocity equation. Notice that unlike before, my velocity equation depends on time squared now, not just time linearly. Now we can take another antiderivative to get y. There will be another plus c, which I'll go ahead and write as my initial y velocity. I don't have to check these boundary conditions because it's a polynomial. I know that it's going to be 0 at time 0. The second term is, as usual, just going to multiply by t. And now I have to do an antiderivative of t squared, which will give me a 1/3 t cubed. Don't forget there's still a 1/2 out here, so I get 1/6 beta t cubed. So that's my first bit of information kinematically, kind of interesting. Now let's go ahead and choose our origin so that x naught and y naught are both 0. It's just convenient to do that. And we'll try to figure out how to calculate the range. Okay, so here are our kinematics equations. I went ahead and decomposed the initial velocity into its x and y components with sine and cosine. So now I want to find the range. Now we could do this a couple different ways. One way would be to eliminate t between these 2 equations and get the trajectory equation. Another way would be to set y equal to 0 immediately. Since we might as well pick up the trajectory equation on the way, I'll go ahead with the first solution method. Solving this equation for t and plugging it in here gives me my trajectory. Notice that the first term here, when I do t, is x over v naught cosine theta. When I plug it in here, the v naughts will cancel out, and I'll end up with sine theta over cosine theta, which is tangent. That term has always been there, even in the old trajectory equation. The new bit is this second term. It's still going to be negative, but now I have a cubic. I've got a 6 in the denominator and I'll have a v naught cubed cosine cubed theta. I could rewrite that as a secant cubed if we want, but let's leave it like this. So this second term is a little different than normal, but okay, it sort of follows what you'd expect, except now instead of an x squared, I've got an x cubed. That means my trajectory is no longer a parabola. You can see that this is going to be a cubic trajectory. And in general, these cubic trajectories are not symmetric. They don't have the same symmetry properties that a parabola does. I don't have a focus or a directrix. In fact, all I really know about it is that when x equals 0, y equals 0. So it starts at the origin as desired. And then it'll rise, it'll have a single peak, and then it'll fall. We can see that because I have a negative cubic term, as x goes to minus infinity, I am expecting it to go down. There's not going to be multiple peaks in there. So the trajectory might look something like this. Okay, so we might want to know some features here. By the way, the rest of the cubic, if you wanted, would have this sort of negative hump down here, which would then go up to positive infinity as x goes to negative infinity. But of course, that's not a physically interesting region. So this thing is no longer symmetric. It's peaked a little bit to the right, we'll see. And we want to know, okay, what is the range? What is the max height? What angle maximizes this range? Let's not forget we have some initial velocity here and some launch angle theta. Okay, to find the range, let's just set y equal to 0 and solve for x. So we're going to set y equal to 0 and solve for x. I'll leave it as x for now. Now, normally solving a cubic would be very difficult, but we got lucky in this case because we can factor out one x. I already know x equals 0 as a solution, so we don't care about that as much. And then I can find an equation for x squared. Notice that factoring out the x and then moving things over will give me this. We can simplify it a little bit. The tangent and one of the cosines will cancel down to sine and a cosine squared. So that is our expression for x squared. Notice that, of course, we only want x. So I'll take the square root of that, and that'll give us our range. Okay, so there's our range equation. Gives us the range as a function of theta. It is messy. It's under a root. There's some weird dependence on these parameters. The units of beta are kind of strange, but that's what we have. So we got our first bit, the range equation. Now let's maximize it. Now I don't like that square root there. It's a little annoying. It turns out, though, that maximizing the square root of a function is the same thing as maximizing the function itself. I'm not going to prove that right here. We've kind of used that before. For example, if you're doing a distance maximization problem and the distance is written as a Pythagorean theorem, square root, no one wants to take the derivative of that square root. But taking the derivative of the square will have the same locations of the extrema. If you're interested, the basic reason is that the derivative of a function squared is proportional to the derivative of the function itself. So if f is a square root, then if this equals 0, this will equal 0 also, so it works. So I'm actually going to maximize r squared just to make life a little easier. Okay, so the stuff in the front is the constant. Now I have to take the derivative of cosine squared times sine. So that's going to be a chain rule product rule deal. All right, so this stuff here we want to set equal to 0. Do notice that there is a cosine. There's one cosine at least in both terms. So I can cancel those out. This one. And I end up with negative 2 sine squared plus cosine squared. That sounds a lot like it could be nicely simplified. So let's rewrite cosine squared as 1 minus sine squared. Doing that gives us 1 minus 3 sine squared, which means sine theta is 1 over the square root of 3. Maybe I'll call that theta star, just so we know this is the theta that maximizes that range. Now, if you want to calculate what theta is numerically, what did I get? 35.3 degrees. Okay, so it's a little more than a 30-degree angle. If you prefer, you could also rewrite this in terms of a cosine or a tangent. Okay, so we have found the angle that maximizes the range in this weird increasing gravity planet. It's an arc sine of 1 over root 3. That's all that Morin asks, but actually let's do 1 or 2 more things. Next, I want to calculate where is this maximum and what is this max height. So let's clear off some of this stuff and go to the next part. Okay, so here is the information that we got previously. We've got our range formula, we've got the angle that maximizes the range. Actually, I just realized, let's go ahead and actually calculate that maximum range. So if I plug in this value for sine, we can see the 1 over root 3 right there comes up for free. Cosine squared can also be rewritten in terms of sine squared. Again, Pythagoras, 1 minus sine squared. So this cosine squared is going to be 1 minus sine squared, but sine squared is a third. And then we've got our sine, which is root 3. 1 minus a third is 2/3. The 2/3 here and the 6 right here cancel down to a 4. And then we have a 4 over root 3. And we could just leave it like that. Okay, now let's go ahead and find the location of this maximum. Maybe I'll call it x star. So we're going to do a little calculus on this thing. We've got our trajectory equation. I'm going to take y prime. Notice that that is the x derivative of y. And it's easy because it's a polynomial. We have tan theta, and then the 3 here will cancel this back down to a 2. Okay. I want to set this equal to 0. And it's pretty easy. We just have that x squared, moving things around a little bit, will be 2v0 cubed cosine cubed theta tan theta all over beta. Taking a square root, taking the positive square root, and simplifying the tan theta like we did earlier. So this becomes a sine, and this drops to a 2. Notice we can compare that directly to the range. It has the same basic structure. The only thing that's different is this 2 versus this 6. So in fact, this is just r over root 3. So instead of being r over 2, like in a parabola where it splits it right down the middle, this is r over root 3. So dividing it by a number less than 2 is going to move it a little bit to the right. Let's also go ahead and calculate this maximal height. That just means taking this value and plugging it right back into y. It's a little messy, but everything should simplify in the end. Okay, like I said, a little messy with all the square roots, but there is some simplification that can happen here. For starters, notice that this piece right here with the roots, we can actually factor that out of both of these equations so that all the messy root stuff is in the front. And then we'll be left with tan theta minus one copy of all this with no root, because we factored out 1 to the 1/2. That leaves a 2/2, which is a 1. And there's a lot of stuff that cancels there. So v0 cubed and v0 cubed cancel. Cosine cubed and cosine squared partially cancel. They leave a cosine down here, but then sine over cosine gives me a tangent, so I get another tangent. The betas cancel. The only thing that's different is I have a 2/6, which is a 1/3. Okay, so this is just going to be 2/3 tan theta. And then I guess it's kind of up to you how much more simplifying you want to do. I probably would bring the tan theta inside, because then I get a cosine squared in the denominator that cancels this. And then I'll have a sine cubed. And that just kind of looks a little cleaner. Okay, there's our expression for the maximal height of this trajectory. Incidentally, and maybe I'll leave this as a little homework assignment, show that the time it takes to reach this maximal point is actually the total flight time over √3, or in terms of these parameters, root 2v0 sine theta over beta. And then this time is actually less, sorry, this time is actually a little bit greater than half the flight time. So it reaches that peak a little later in the trajectory than it would for a parabola. Okay, so to summarize, I know there's a lot on the board. We have found the trajectory equation, the range, the angle of maximizing the range, the max range itself, the height, and the, or I'm leaving for you, the time it takes to reach that max height. And we also found the location of this maximum height. And we can see that although there are some similarities with what we saw with the standard projectile motion, it's got some differences. It's a little bit fun. And as one final thing for you to try out, see if you can find the angle that maximizes the height of the projectile as opposed to its range. Second little homework assignment. So we've studied this problem in great detail, found a lot of the parameters. I think we can say this one's pretty well done. QED.